The mission of the aerodynamic group at Cameron is to provide the most effective compressor design possible. This is no small task, as the definition of effectiveness varies from customer to customer. For one customer, effective may be the lowest power consumption. For another, effectiveness may mean operating at extreme pressures or flows. Whatever the application, we are dedicated to providing the most efficient design that meets and exceeds your performance criteria. A compressor is made of one or more stages combined in a series, each of which may or may not be intercooled. Stages on a gearbox are driven by a common bull gear that in turn is connected to a primary drive source, a motor or turbine. The compressor stage consists of three fundamental components: the impeller, the diffuser, and the scroll. The impeller is responsible for imparting work into the gas stream. While it may seem counterintuitive, the purpose of the impeller is not to increase the pressure of the system. Instead, the impeller is used to transfer kinetic energy into the flow field by increasing the speed of the gas. As the gas exits the impeller, there is some rise in pressure. However, most of the energy transferred to the gas is in the form of increased speed. The challenge in the design of the impeller is in efficiently accelerating the gas while minimizing losses. The next fundamental component, the diffuser, serves a dual purpose. First, it converts the kinetic energy or velocity into potential energy or pressure. As the fluid particle proceeds through the diffuser, velocity decreases and static pressure increases. Again, the designer tries to accomplish this with minimal losses. The second objective of the diffuser is to act as a coupling device between the impeller and the scroll volute. Quite simply, the diffuser prepares the flow field coming off of the impeller for collection in the volute. The third primary component is the scroll, that is responsible for collecting the fluid in the radial direction and redirecting it back into the axial direction with minimal loss. Scroll performance is dictated by the gas flow angle into the scroll and whether the flow is accelerating or diffusing in the scroll. Optimum scroll performance occurs when the collector is neutral. That is, the average flow is neither accelerating nor diffusing as it moves towards the exit conical diffuser section of the scroll. The best performance for a specific application results when the performance of all three components are analyzed together. It is the synergy of these three components, coupled with the customer design requirements, that is the focus of Cameron's aerodynamic design effort. Aerodynamic design technology has made great strides throughout Cameron's 50-year history. We have progressed from radial impellers with vaneless diffusers to custom 5-axis impeller designs with matched low solidity diffusers. During this journey, the science of rotodynamics has matured, allowing the engineer the flexibility to select the optimum speed for the compressor. In 2005, Cameron made a milestone commitment in the area of computational fluid dynamics by investing in a team of experts using state-of-the-art design tools. The objective of this commitment was to enhance our understanding of the compressor flow field. In turn, this new, accurate picture will provide the foundation for all future development. Implementation of CFD faced two major hurdles. The first was the computer hardware requirements. Only a few years ago, the complex calculations used daily while designing compressors would have required one or more mainframe computers. The runtime needed to process that type of job would have taken months or even years. As a result, CFD were not conducted. Today's desktops are well beyond yesterday's mainframes. Hardware has developed to the point that processor speed and memory requirements are no longer an impediment, making CFD calculations possible in acceptable time periods. The second major challenge to implementation was software development. While the equations governing fluid flow have been known since 1822, the models necessary to convert these differential equations into computer code were primitive. Models have matured over the years and are now at a level where the results they are providing are consistent with the test data. Today, Cameron's compression group at Buffalo utilizes state-of-the-art CFD on all production and development work. Our aerodynamics department maintains a high-performance Linux cluster farm consisting of 37 high-end workstations augmented with a 16 CPU Linux server. Resources for this farm are controlled using a load-sharing facility program. Using this scheme, our cluster is effective 24 hours a day, 7 days a week. For any given project, our design team performs multiple and extensive CFD analyses for each impeller design. Additionally, the engineer can perform analyses on the combined impeller diffuser set, something that has never before been implemented on a production scale. The The lessons learned from CFD are being incorporated into today's technology. Whether it's improving the flow field inside the impeller, optimizing recovery inside the diffuser, or mitigating losses in the collector, Cameron is actively engaged in improving the performance level of our compressors in order to minimize operational cost. And not only does one see this benefit on new machines, but the potential exists to incorporate new technology on existing hardware.